Hey everybody, let's talk about Kepler's laws. There's three of them, and one of the things I also would like you to do is look up Kepler. There's books about him and all kinds of things about Johannes Kepler. He was an amazing human being, really interesting guy. Lived in the late 1500s, early 1600s. Was a contemporary of Galileo, and he through empirical methods, that is just by looking at particularly the orbit of Mars, he was able to figure out a mathematical description for how planets move around the sun. And in those days, it was kind of dangerous to believe that planets moved around the sun, but he believed it, and he showed that it was true, and he described exactly how planets move around the sun, and he described that in his three laws. So let's go over the first law here, which basically say the planets move in elliptical orbits with the sun at a focus. And let's show this here. I've got a piece of cardboard, and make it. If you're going to do this at home, make it several layers thick so you can actually get the push pins to go through it. And so here's a loop of yarn. And let's see, stick one in like that, all the way through, and take another one. So the first time I did this, I made the two foci too close together. So anyway, there we go. And now you can make an ellipse. So you've probably done this in geometry and so on, but it's kind of fun. And there's our ellipse. Go around a few times, make it nice and dark. So there's our ellipse. And now this is a fairly eccentric ellipse, at least compared to the orbit of a planet. And what he said is, okay, planets move in an ellipse, and here would be the sun. Okay, the sun is at one of the foci, right here. This I should have used a different piece of cardboard because this was a mistake right here. But anyway, here's the sun. Now what's over in the other foci of the ellipse, the other focus of the ellipse? Nothing. It's empty space. And my planet goes around like this. Maybe this is more like a comet's orbit. It goes really slow out here. And then as gravity pulls it in, it goes really fast. And then it slows down, and then really fast. Okay, so that's how a planet moves around the sun. So it moves in an elliptical orbit with the sun at a focus. And let me just draw it like this. Okay, here, let's draw an ellipse. And here's the sun. And here's the semi-major axis and the minor axis. And here's the other focus. There's two of them. And here's what what else he said is that as the planets move around the sun, so the second law basically says that a planet will sweep out equal areas in equal times. Okay, so let's say the sun's right here, and here's our ellipse. Let me erase this thing right here. And here's my satellite. Again, it could be a spacecraft, could be a planet, whatever. Here it is over here. And it's going to move. As time goes by, it kind of moves a little bit. And if you think about what it sweeps out right here, it sweeps out an area like that. And he observed these areas. Now, by the way, it took Kepler 20 years or something like that to do what I'm going to do in 20 minutes. Okay, if he could have watched this lecture, he would have cried. Okay, but you know, hey, I've got Newton on my side and I got a textbook on my side, you know, so lucky me. But anyway, here's the sun, and notice that this little wedge shape has an area. And notice that when you're really far away, this is a skinny little wedge. But when you're really close, the wedge shape is going to be wider. Now, what he said was that, let's say this takes a month for this planet to go from here to here. Well, the area of this has got to be equal to the area of a wedge that would be over here. So let's say the planet was here and it's going to go over here in that same period of time. So he said that the area of this has got to be equal to the area of this if the planet is moving around the sun. Equal areas and equal times. Well, I think you can see that if you go from here to here in a month, or if in a month you go from here to here, you're going a lot faster over here, and that is true. The closer you are to the sun, here's what happens. Think about it conceptually. You're way out here, you're a planet, you're moving, and then all of a sudden you feel that tug of gravity and it pulls you down, but you're not in a circular orbit, so there is a component of the gravitational force that's tangential to your path that's going to make you go faster and increase your speed, increase your speed, increase your speed, and you're really hauling through here, and now the gravity is slowing you down, slowing you down, slowing you down, slowing you down, slowing you down. Really, you go your slowest out here, and you go right here and you speed up, speed up, speed up, speed up. So you kind of go whoosh, whoosh, like that. Okay, actually, in space, there's no whoosh, but I think you can tell what I'm trying to do here. Well, let's prove this. Kepler didn't really prove it, he just observed it. He said, hey, I noticed that this is true. So what he did was, he said, well, here's what I'm going to do. Anyway, notice something here. Here's the sun, and here's my spacecraft, okay? And it's going to pull on it with gravity. So here's my force. And here's my position vector r from the sun out here. So here's r. Now, what did we say about torque? Let me zoom out a little bit, make more room. Well, we said that torque is equal to two things. It's equal to r cross f. And we also said that torque, that at least the net torque on an object, is the rate of change of angular momentum. Okay. Well, notice that this cross product right here is, well, it's going to be 0. Can you tell me why? Why would r cross f be equal to 0? Well, think about the definition of cross product. It's r times f times the sine of the angle between r and f. What is the angle between r and f, no matter where you are in orbit around the sun? Well, let's see. Here's r, here's f. Here's r, here's f. It's 180 degrees. The angle between r and f is 180 degrees. And what's the sine of 180 degrees? It's 0. So the torque is going to be equal to 0. Therefore, L equals a constant. So we can say that the angular momentum of a planet as it goes around the sun doesn't change with time. It's conserved. So we're going to use that to our advantage here in a minute. Now, one of the things I can do is looking at angular momentum. I mean, angular momentum is equal to r cross p, recall, where p is the linear momentum. Let's look at the object when it's right here. So it's right here. So it's got a velocity vector like this. It's got a certain mass, m. And of course, here's r right here. There's my r vector. Well, one of the things that you should know about when you about cross products is that when you have A cross B, the magnitude of A cross B is the area of the trapezoid, not the trapezoid, the parallelogram made between A and B. So if here's A and here's B, A cross B turns out to be, well, if we make a parallelogram out of this, let's put another B on here. So here's another B, and then we'll put A up here. So A cross B, it turns out that the magnitude of A cross B is the area of a parallelogram. Now, just accept that, okay? Now, look at the area right here. Here we have, if we look at R cross P, here we have R cross P, but let's take a look at the area of this shape that's made by R cross P. Well, hold on a second. Let's instead of V, let's take a look at this. This is R cross MV. Okay. Well, let's expand this out a little bit. R cross M, and what is V? V is dr dt, right? The rate at which I change my position. This is my position from the sun. This is the rate at which I'm changing my position. And I want to look at the cross product between R and dr. Okay, so R cross dr. Okay, well, if this is dr from here to here, and here's R cross dr, I really get the area of this little wedge shape here. Now, dr is an infinitesimal. So what this is, though, R cross is twice the area of this little wedge, the area of the wedge that I sweep out. I'm going to call that dA. Okay. And of course, an area has a vector when you sweep from R across dr. But now, so this is the area of the wedge that I sweep out in a little bit of time, dt. Okay, so so what I can do is I can say that dA is equal to what? R cross dr over 2. Okay. Well, now what I'm going to do is I'm just going to kind of get back to where I started. Let's divide by time. dt. dt. And now, I want to say something about the rate at which the area is changing with time. I'm going to multiply top and bottom by the mass here. Why? Because it's convenient to do that for the proof that I'm doing here. So let's multiply this by mass and multiply this by mass. We're allowed to do that. But that's dA dt. So the rate at which I change the area, the rate at which I'm sweeping out area as I go around my ellipse, is equal to R cross M dr dt. But what is dr dt? It's V over 2m. Okay. But what is this right here? R cross mv. That's my that's my angular momentum. This is L. So this is going to be L over 2m. Okay, so, wow, you're thinking, hope you followed all that. It's kind of cumbersome. But let's think about what this means. The rate at which I sweep out area as I go around my ellipse is equal to my angular momentum divided by twice the mass of my little dude here. But because there is no torque on the gravity does not apply a torque to my planet. We're saying that the angular momentum of my planet is constant. Well, that means that this is a constant. Well, 2 is a constant, and the mass of my planet is a constant. So L over 2m is a constant. Well, if the derivative of something is a constant, well, actually, hold on a second. This is what, I mean, we've done it, actually. We're saying that the rate at which I sweep out area is a constant. And that is Kepler's second law. So we're done. Now, I did this in a few minutes, right? And it took Kepler a long time, many years to figure this out. Why? Because I have the mathematics of cross products, which Kepler didn't have. I have the concept of angular momentum and torque, which Kepler didn't have. So I think you would have enjoyed seeing this. But there it is, equal areas in equal times. Now, let's go to Kepler's third law. So Kepler's third law. Now, in this one, he would really cry if he saw me do this. And actually, you know what? I'm not gonna do this as a complete form. I'm not going to do this for an ellipse. I'm going to do this for a circular orbit. Kepler's law does this for an ellipse. And if you want to know how to prove Kepler's third law for an ellipse, take upper division mechanics when you get to college. You will work in that class what's called Kepler's problem, and you will prove Kepler's third law from using Newton's law of gravity for elliptical orbits. But that's a little bit beyond the scope of this class, so we're going to do it for circular orbits. So let's take a look. Oh, well, first let's state his third law. Here's what Kepler said. He said T is the period of the orbit is directly proportional to the cube of the semi-major axis of an ellipse. Okay, this is what he said. Take the period of the orbit. Now, what is the period of the orbit? The period of an orbit is the time it takes to go around the sun one complete time. Now, what is A? A is the semi-major axis of an ellipse, which is from its geometric center right here out to the maximum extent of the ellipse, or from here to here, here to here. And he called it A. Well, we're going to call it A. Your textbook calls it A. Okay? So that's the semi-major axis. Now, if you take the two foci and you collapse them to the same point, the ellipse turns into a circle. So if you do this for a circular orbit, so let me try to draw a circle here. Okay, there's a circular orbit. Your semi-major axis is actually the radius of the orbit. Okay, and let's prove that this is true. So what we're going to prove actually is that the period squared is proportional to the radius of the orbit cubed. Because, I mean, and really Kepler did this for circular orbits, because, yeah, Mars has an observably eccentric orbit, but the other planets that he could observe, and this is before the telescope, right? Kepler wasn't using telescopes. The orbits of Mercury and Venus and Earth and Jupiter and Saturn, those are the visible planets that Kepler used. Those planets all have, except for Mars, which is observably elliptical, the others are just circles. I mean, yeah, they're really ellipses, but when you really look at them carefully, they still look pretty circular. But anyway, let's do this. Well, here's my orbit, And I'm going to use an idea that Kepler didn't have, and that's this law of gravity here. So here's my little mass m. Here's my big mass. This is the mass of the sun. This could be the mass of Mars. And it's moving in a circle, right? So we've got so this force of gravity, which we know is Gmm over r squared, right? Okay. This is going to be equal to a centripetal force, which is mv squared over r. Remember, we did this before when we developed the orbital velocity equation, right? You just take this equation and solve it for v, and you've got the orbital velocity. But what we're going to do is change this a little bit to show that this is true right here. Well, first of all, let's get rid of the mass of my spacecraft or my moon or planet. It cancels out of the equation, and it really only depends on the mass of the sun. Now what I'm going to do is I'm going to make this observation that the speed of the planet is constant as it goes around its circular orbit, and the speed of the planet is equal to the distance divided by the time. Well, if the distance is 1 time around, that distance is 2 pi r. And if the time it takes to go around 1 time is called the period, well, then my speed is the distance divided by my time. The distance around the sun divided by the period, which is the time it takes to go around the sun. And now I'm going to substitute this in here. So let's do that. We get Gm over r squared is equal to this squared, which is 4 pi squared r squared over the period squared. And then, of course, we have this r right here. So this r will cancel with that. And what I'm going to do now is just solve for the period squared. And we're just going to cross multiply this times this divided by that, right? So the period squared is equal to this times this, so that's 4 pi squared, and this is r squared times r, so that's r cubed divided by this. I've done it. I have shown that Kepler's third law is true for circular orbits. Because look, 4 and pi squared, and g, the gravitational constant, and m, the mass of the sun, is a constant. These are all constants. And so if I just say, so that means that the period of my orbit squared is directly proportional to the radius of my orbit cubed. We did it! Kepler's 3 laws. One thing that's really cool about this equation is that you can, if you are observing a large object out in space, and you can observe something in orbit around it, if you can measure the orbit, and if you can measure the period, you can solve for the mass of the object. Isn't that cool? This is how we measure the mass of black holes. They see stuff moving around the black holes, and they have an idea of what the radius of that is, and they measure the time, and they can solve for the mass of the black hole, or any object. This is really basically how we measure the mass of the planets. We observe their moons in orbit around those planets, and we use this calculation to solve for the mass. Anyway, Kepler's 3 laws of planetary motion. Let's just repeat them. First law, we've got planets moving around, or comets or asteroids, anything, moving around the sun with elliptical orbits. They sweep out equal areas in equal times. Okay? And that means, of course, that planets are moving, if this is the sun right here, and there's nothing right there, planets that are far away move slower than when they are close to the sun. And then, of course, Kepler's third law, which says that the period squared is proportional by 4 pi squared over gm to the radius of the orbit cubed. And we proved this again for circular orbits. I leave it to your future college career, if you take more physics, to show that this is also true. If you replace r with the semi-major axis of an ellipse, it is also true for elliptical orbits. So that is all.